life appear at the beginning of December, and from 14th to 31st December, the ozone layer was formed, and all kinds of plants and animals came to life, including trees, insects, reptiles, mammals, birds, flowers, dinosaurs, apes, and human beings. And some of them have already are extinct so far. So this is as far as we can go on this cosmic calendar, and then I would like to go back to the oxygenation, the great oxygenation period, the time when the oxygenation of the atmosphere occurred, and nature, in its infinite wisdom, created what has become to be known as the ozone layer. In short, when the oxygenation of the atmosphere happens, there was enough oxygen to start forming the ozone layer through a very simple process. Oxygen, as we all know, has two atoms, and whenever a molecule of oxygen is hit by ultraviolet rays, it forms into two, it splits into two, and form two atomic oxygens, which are freed, and then this atomic oxygen combines with another molecule of ozone, and then you have the O3, which is the ozone, as we know it, the molecule of ozone. And this is a continuous process that goes on and on and on. So the ozone is naturally produced in this process, as you can see in this in this two-step continuous production cycle. It is even hard for us to believe that this fragile system, which is permanently destroyed and created, can protect us from this harmful rays of the sun. But this process of the creation of the ozone layer, as we know it now, happens maybe around 400 to 600 million years ago, and precisely with that, the migration of life started from the sea into the land, and now allows us to live on the planet Earth. So again, this ozone in the stratosphere is what we call the ozone layer. And this is the way the ozone layer looks right now. The ozone concentrations are greatest between 15 and 35 kilometers, where the range with the density in those regions varies from 2 to 8 parts per million. And if all of that ozone layer were compressed at the level where we are now in Trinidad, if all were compressed under the pressure conditions here, it will be very thin, like any coin that you have on your pocket now. So I'm going to go into the history of the discovery of the ozone layer and the man-made gases that destroyed the ozone layer. So the ozone layer was only discovered by 1913. We're talking of less than 1 century ago, by the French physicists Fabry and Buisson. Its properties were explored in detail by the British meteorologist Dobson, who developed a simple spectrophotometer, the Dobson meter, that could be used to measure the density or the ozone layer. Mr. Dobson was fantastic. During his lifetime, he managed to develop a big network of ozone, of Dobson meters, stations around the world, which still are in functioning, and that became like the most convenient way to measure ozone around the world. And we measured the ozone in terms of Dobson units that are in his honor. I know that I am going to go into a bit of details, and I hope that you will not fall asleep in my presentation. But I want to do a kind of a deal with all you. I know that several of you have been meeting all day long, this and so if I see any one of you sleeping, I will call your attention. If you see me falling asleep, you have the authorization, absolute, to call my attention too. So that's a deal to begin with. So I would like to now go back to the last day of this cosmic calendar and focus a bit on the human history, which is basically the last day of this calendar. If you can see, at 22 hours, 24 minutes, the primitive humans and stone tools emerged. Anatomically, modern humans came about 23 hours and 52 minutes. And now I would like to focus on the last minute of the calendar. Agriculture only started 23 hours, 59 minutes, and 32 seconds. You are producing very good agricultural engineers here and agronomists. And so they have been only working for the last 28 seconds in this cosmic calendar. The birth of the first writing was on the 47 seconds. At 48 seconds, there was the first dynasty of Egypt and the invention of the astronomy. At 49 seconds, the alphabet and the wheel were created. And at 55 seconds, the Roman Empire was at its height. And at 23 hours, 59 minutes, and 59 seconds came the Industrial Revolution, modern science and technology, the American and the French Revolution, the World War I and II, the Apollo moon landing, and the development of the internet, the iPods, the iPads, and everything that is now being produced in China by tens of millions was invented in the last minute, in the last second of this cosmic calendar. So, the discovery of the ozone layer happens in that last second, and as we will see, in this short history of the humankind history, it's just amazing what the human beings have been doing. All this that happened in the last second have a tremendous impact in our life now. We live much more comfortable than 400 years ago, certainly. And all this development always, or unfortunately, sometimes comes with a price. And this price, in the terms of the ozone layer, is being paid by this huge and rapid pace of development. So, by all standards, this massive accumulation of knowledge and this monumental development of new technologies and industries on Earth has a price, and this is the story that I am going to tell you now. The price that has been paid by the ozone layer with this pace of development. I told you before that what was the ozone layer and was discovered just less than 1 century ago, and now I would like to take you through the man-made, through the invention of the man-made gases or chemicals that were referred to as miracle gases at their invention. These were discovered by a Belgian scientist in the end of the 19th century, and he pioneered, this scientist, Frederick Schwartz, pioneered the synthesis of CFCs. Then an American chemist and scientist team led by Charles Kettering developed some of the first CFCs to be used as refrigerants and aerosol propellants. And Thomas Mingley Jr. was a key figure in that team and was the one that improved the synthesizing of the production of CFCs to enable the use of them as refrigerants. So CFCs were hailed as the wonder chemicals and were used in many applications. You name it, they were used in many, many applications. Some of them are in this slide. So in the 1930s, those chemicals started its commercial use. And it took around one generation to discover in the 70s that these wonder chemicals were damaging the ozone layer. So by 1970, there was already research, and the sound alarm was run by scientists about the possible destruction of the ozone layer by man-made chemicals. Paul Crutzen in the 70s demonstrated the loss of ozone due to ultrasonic aviation, supersonic aircrafts. And in 1974, Sherwood Rowland and Mario Molina published a paper in the Journal of Nature that you referred to, hypothesizing that when CFCs reached the atmosphere, the stratosphere, they were broken by UV radiation, ultraviolet radiation, and from the sun, and this was releasing the chlorine atoms that were beginning to destroy the ozone layer. By the way, one chlorine atom alone can destroy more than 100,000 molecules of ozone. Of course, they were asking at that early time, 1974, to a complete ban of the production and use of CFCs. However, like in many other scientific discoveries, skepticism from other scientists and from commercial manufacturers persisted for some time after this initial discovery. Several research papers follow these seminal papers of Rowland, Molina, and Crutzen, and in 1976, the U.S. National Academy of Science published the first assessment report on the ozone layer conditions that confirmed that the ozone depletion threat from CFCs confirmed that threat and concluded that action to regulate the CFC use should be global in order to be effective in the long run. International consensus was starting to build on the need to address that issue. And if I have to say that these three scientists were recognized later on, the Nobel Prize on Chemistry for their seminal research and the important work that they did to mobilize the international community. Science indeed was leading the way, and the international negotiations were launched under the auspices of the UNEP. And they were launched in two steps. Let me tell you first about the adoption of the Vienna Convention for the protection of the ozone layer, and later about the adoption of the Montreal Protocol. In 1977, the UNEP was requested to produce a plan of action focusing on the study of the phenomena. And several years later, after continuous research by the global community, the scientists around the world, UNEP was again requested by the governments to initiate the negotiations for leading to an international treaty. And this is how the Vienna Convention was agreed under the auspices of UNEP in 1985. At this point, I would like to say that this agreement of the Vienna Convention is a real shining example of the use of the precautionary principle in the international negotiations. There was not complete evidence that the ozone layer was being destroyed. There was not a clear evidence. There was not, it was contested by many other scientists that there was no destruction of the ozone layer at the time. However, the international community managed to agree on the convention of the Vienna Convention, the Vienna Convention for the protection of the ozone layer, in spite of lack of certainty, full certainty. And this really, as I said, shines as the first example, real example of the use of precautionary principle to move forward on international global action. During the negotiations of the Vienna Convention, however, more research was made available to the general public. And very importantly, at that time is that when scientists came with the concept or the discovery of the ozone layer. It was firstly presented by a scientist, by a Japanese scientist, Kubachi in 1984, followed by another publication by the British Antarctic survey scientists Farman, Gardiner and Shanklin, that was again published in the magazine Nature in 1985, in May 1995, where they were announcing that there were large depletion of the ozone layer in the Antarctic during the Antarctic spring time, at least since 1981. And satellite measurements at the time were again coming out with the same type of measurements. There is an interesting piece of information here that I would briefly like to share with you. The satellite measurements were going around for many years before 1985, because satellites started providing us with this information in the 60s and 70s, certainly very profusely. However, these satellites are functioning on software that is designed by humans, and then there are thresholds on those softwares, and the thresholds that were on the measurements of ozone had a maximum allow a maximum depletion of 50%. Further, more than 50% was just cut off the algorithm because of large mistakes. So that's why the measurements on satellite were not being able to detect the ozone hole at the time, and it was only with this work of Kubachi and the British scientists that the measurements of the satellite measurements were rerun, and then they managed to show that indeed, as early as 81 or even the 70s, there was this ozone hole being produced in the Antarctic. We have been using these pictures on the left to measure the ozone hole. Very briefly, I just want to say that this is in the 70s, but this is in the 80s, and this blue color represents the size of the ozone layer, of the ozone hole in the Antarctic. The red ones were quite good in the 70s, 70, 71, 72, and 79, but in the 80s, really, the process started very clearly to show. And the term ozone hole was first used by Roland, Sherwood Roland, in one of his media accounts, and since then we have been using the ozone hole as this concept of the ozone hole. It pictures a fantastic image in the mind of all human beings. And maybe this is what is lacking in some other treaties, the lack of a clear image that will determine the world to act in other global problems. The understanding of the ozone hole were further the research and many other very interesting papers were published. And I want to refer specifically to this research done by Susan Solomon because she discovered how actually the ozone hole was formed. She discovered that, under the cold temperatures, there was the formation of these crystals, the polar stratospheric clouds, that were considered, that were like a surface on which ozone was trapped, and one chlorine molecule could become a serial killer on the top of these crystals. And this is, first of all, the first explanation of why the depletion was so huge in the Antarctic. But she also demonstrated that because of the special conditions in the Antarctic, there is, every springtime, there is a formation of a vortex that virtually isolates all the air on top of that area, and there is no influx of new air from outside this vortex. So all the air there is massively destroyed, because the air is there quiet. It's like it becomes all, and the scientists refer to this air there as all air, age air. And she came up with all these theories that were later on confirmed in the laboratory and in the natural, in experiments also on the South Pole. Okay, now it's enough of science. I was hoping that there were going to be many students of science here in the university, and I see many now. But I would like to move now from the science to the international efforts to actually control or regulate the substances that deplete the ozone layer. 2 years later, after the approval of the agreement of the Vienna Convention, the international community managed to negotiate the Montreal Protocol on substances that deplete the ozone layer. And this international treaty, negotiated under the auspices again of UNEP, the United Nations Environment Program, and it's very simple, the objective. It requires the reduction and eventually the total phase out of the substances that deplete the ozone layer. That's the objective of the Montreal Protocol. So it regulates the consumption, the use, the production and consumption of these substances that deplete the ozone layer. And as I said before, those substances were widely used in different applications. I mean, and we were in contact with products produced by those substances since we were sleeping, waking up, and working. We were always in contact with these products produced with ozone-depleting substances. So the challenge to phase them out or come up with new technologies was really big in 1987 when the governments of the world agreed to this Montreal Protocol. And now I would like to talk about the achievements of the Montreal Protocol, and then I would like to take you what is behind these achievements and see and then we can later discuss or answer any questions. So, some of the achievements of the Montreal Protocol. First of all, I would like to say that the Montreal Protocol and the Vienna Convention are the only treaties in the world, in the history of humankind, which is, as we saw before, short, are the only treaties that have achieved universal ratification. And this is a tribute of what I said before, that global challenges, environmental challenges, need the participation of the global community. And so this milestone of universal ratification is quite a tribute to all the governments of the world. And so this graph, you will see that we have 196 parties that have ratified the Montreal Protocol. Just as a reference, the United Nations General Assembly of the United Nations have 192 parties, and the other multilateral environmental agreements may have 193 parties. So we feel very proud of this achievement, and we're still working. The other curves there are the amendments to the Montreal Protocol, and we are targeting to get also the universal ratification of this